We're going to look at a couple of examples of finding symmetry. The three symmetries that I'm looking for are origin, also known as a rotation of 180 degrees around the point 0, 0. We're going to look at y-axis, and we're going to look at x-axis. And what I like to do is I like to start off with attempting to find a counterexample. If you find a counterexample, you've proven that something does not have symmetry. So let's start with basic rules here. If you have the point x, y, in any case, if it has origin symmetry, then it will also have the point negative x, negative y. I like to think of that as opposites give me opposites. Y-axis symmetry, again, we're going to have x comma y for points. Try that again. And that will also have negative x comma positive y. Again, if you plug in opposites, you get out the same value. And then for x-axis symmetry, xy, the same x also gives out a negative y. So those are the scenarios. So if I can show that none of those exist in a given scenario, then I can prove that it doesn't have those three symmetries. It might have some symmetry, but those are a little bit more complicated. So I'm going to pick a value for x that I like to plug in. So in this case, I can't plug in -2, and I can't plug in +3 for a couple of different reasons. If I can't plug in -2 because the function is not defined there, and I can't plug in +3 because the value of the function would be 0, and 0 has no sign, therefore checking to see if I'm getting out opposites doesn't really work. So I'm going to choose 1. 1's a nice number. I'm going to see what I get out. If I plug in 1 minus 3 over 1 plus 2 squared, that gives me -2 over 9. So -2/9 is the value of the function at 1. What about at -1? I'll do that in a different color so it kind of stands out. Do blue. -1. So -1 minus 3, -4 up top. -1 plus 2 squared is 1, so I get -4. And you can kind of clearly see, or hopefully you can clearly see, that opposite inputs do not give me opposite or the same value outputs. So in this case, this is proof enough. This is a counterexample. Counterexample for each of those symmetries. So this function has none. None of the key symmetries. Okay? Get rid of that. Let's go to the next page. And let's try this function. Again, I'm going to try to show that there's a counterexample. So let me try 1 again. If I plug in 1, I have 1 cubed minus 6, which gives me -5. If I plug in -1, -1 cubed minus 6 times -1 actually gives me +5. So I'm really looking to see if there's anything that I can get rid of. So by plugging in opposites, if it were even, also known as reflection over the y-axis, the answers that I got out would have been the same. And since they're the opposites, this is a counterexample for R, or reflection over the y-axis. But if you look at it, we plugged in opposites and we got out opposites, That's an instance for origin symmetry. So what I then do, once I find an instance, then I try to prove it algebraically. So we know that xy and negative x, negative y would show origin symmetry. So what I'm going to try to do is now prove that. So in my function, instead of x, I'm going to use negative x to see if the results are exactly opposite of my original equation. So I'm using function composition, negative x in for x in my original function. Again, this is something that you should probably already know from pre-calculus or previous lessons in pre-calculus. When I cube a negative, it stays negative. If I multiply negative x times negative 6, I get positive 6x. And you can see that these are opposites, but what I like to do, especially since not everyone can see that, I'm going to keep the y, I'm going to drop down, but I'm going to factor out a negative 1. And when I do, I get negative x cubed minus 6x, which literally means the opposite of the original, which to me is proof that this has origin symmetry. Lastly, we need to prove that this has x-axis symmetry or not. And since this is a function, they do not have x-axis symmetry. So let's check to see if we can find another one that might have some different symmetries going on. So we can check. Let's try this one. Let's try to show that it doesn't have origin or x-axis by plugging in 1 in for x. 1 in for x would be y squared equals 4. And if we plug in, if we square root, we get, plus or minus 2. This should be an indicator that something different is going on. Okay? In fact, xy and x negative y, same x, opposite y's, not a function. Okay? Let's plug in negative 1. What do we get out for negative 1? So we have y squared equals 2. We can square root that, and we get plus or minus the square root of 2. So clearly, what you should recognize here wow, that's too dark. What you should recognize here and here is that these are each counterexamples I'm going to just shorten it to CE, counterexamples for origin and y-axis. Why? Because when you plug in opposite values, you need to either get the same number out or opposite numbers, and clearly when I plug in 1, I get plus or minus 2. When I plug in opposite of 1, negative 1, I don't get plus or minus 2. So those are my counterexamples there. But now we need to try to show this. So, whereas trying to prove odd or even, we plug in negative x, here we're going to plug in negative y. So negative y squared equals x plus 3. And what we're going to try to show is that it doesn't matter what x is. And when I square this, I end up with the same exact function as before, which is proof that it has x-axis symmetry.